Brian.
Hey Peyton, how are you?
I'm good. How are you?
I'm doing fine. I have two midterms this week, one on Thursday, one on Friday. Just got home from an event of like games, like musical chairs, dodgeball. I'm really tired right now.
Wow, that sounds so
Yeah,
fun.
yeah, it was fun. hmm Hello, hello. Hey, so. We could get started with 118B stuff, and then we could do 8B after. Um, Peyton, did you have a question or topic you want us to go over for 118B first?
Yeah, I was wondering if you can go over the post lab stuff that Crystal sent you last. I mean,
Yes.
yesterday.
Yeah. Let's go over those. Um, I can go over post-lab H Diels-Alder. Yeah, I think that's the one that Crystal sent yesterday. I went over the first one last night, so that is on YouTube. Um, So there's like three more of those. So I'm gonna do that right now. Okay. Okay, the second one was given like this, where we have this diene with this dienophile. And we see that this is the diene part of the molecule, the yellow highlighted part, and this is the dienophile part of the molecule. So I'm gonna redraw this in the orientation where I'm used to seeing it, where the diene is in this form and the dienophile is in this form. So this is the yellow highlighted part, this is the blue highlighted part. Now everything else is going to be copy and paste like that. And we notice that this dienophile here is trans, right? So because it's trans, we have to make sure that we draw it trans as well, like this, right? Where one group is going to be an acetone and another group is going to be like a ketone with one extra carbon, like this, like CH2, CH3. And the regioselectivity here matches up because there's an EDG here. So there's going to be a partial negative charge on both carbons, EWG here, EWG here. So there's going to be a partial positive charge on both carbons. So one of the products will come from this orientation. Another set of products is going to come from this orientation right here. Right, where I just flipped the dienophile upside down, but the charges still align, right? There's still a partial negative charge here and here, partial positive charge here and here. Now, once I align those charges, I then draw the pocket between the diene and dienophile. Then once I draw that pocket out, I identify my out groups, in groups, and EWG. This is my out group because it's outside of the pocket. This is my in group because it's inside the pocket. And these are my EWGs, electron withdrawing groups on the dienophile. Now, when we do the mechanism, I'm going to number this atom 1, 2, 3, 4, 5, 6. Do the whole mechanism, which is always going to give us this product for Diels-Alder. Is the partial charge equal on both methyl and ethyl? Yes, the partial charge will be equal for both methyl and ethyl. There's going to be a little bit more negative charge on this end because the ethyl is more bulky than the methyl group, so it's going to donate electrons a little bit more than the methyl group. But in the post lab, it doesn't really make a big difference. Just think about it like how, since they're both R groups, there's gonna be both equal negative charge on both sides, right? If, however, like there was an OR here, this right here would be a stronger EDG. So we're gonna donate electrons way more strongly. So there's gonna be a negative charge more on this end here, if this was an OR group right there. But because these two are R groups, there's gonna be negative charges equally on both sides. Where this is gonna be atom 1, 2, 3, 4, 5, 6. This is the yellow highlighted part. This is the blue highlighted part right here. Now, based on the endo rule, the out group is cis to the EWG. Do we need to flip the molecule because the either group can be attached to either side? Yes, we need to flip the group because either group could be on either side. Like there's equal negative charge here, here, and equal positive charge here and here, right? And because there's equal charges on all of these carbons right here, then we have to flip them because they're gonna give us different answers, right? That's that. So I'm gonna make the out groups here dashes, right? Which makes oh, this is gonna be an interesting one actually, because notice how these EWGs here are trans to each other. We have to choose one of the EWGs to follow the octet rule. So there's gonna be like 2, 4, 6, 8 products. Let me double check this though, because that looks so wrong. Let me see my post lab here. Let's go. H post lab questions. Yes. Okay. Yeah, on my post lab, I had the same exact question, but I just drew out one of the answers. I didn't like flip one of them, but this one looks wrong because it is cis to each other. So let's say that this EWG here is going to be the one that follows the octet rule, the endo rule. So that's going to be dash with the out group as well. But this EWG on the other end has to be a wedge because these two EWGs here are trans to each other, right? And we still have the in groups connecting the carbons 1 and 2 right here, which is this in group right there. So that's going to be one of the products right there. But we could have said that the EWG at the bottom follows the endo rule, which is going to be dashed, making this EWG at the top a wedge. Plus minus like that. Right? Because the dinophile here being trans makes it more complicated. The out groups are going to be cis to the EWGs, but these EWGs here are trans to each other. So at this top set of products here, the thing that follows the endo rule is that EWG. But at the bottom set of the products, this EWG here follows the endo rule. Because these two EWGs has to be trans to each other. Right? So those are the first two sets of products. We could do the same over here. Dash. Wedge. Dash. Like that. Plus minus. So I would double check with your TA with this one, because this one is like 8 sets of products. Here, like 4 sets of enantiomers. Right. But any questions on how I got these 4 sets of enantiomers here? Right, this one is a difficult one. This one here gives us 8 answers. And I know Mira Jones' worksheets has some problems that gives you 8 different products like this too. Right, so this is one set of products, another set of products, another set of products, and another set of products. So 4 sets of enantiomers, 8 products total. Okay. Now let's move on to the next one, which is going to be this diene reacting with this molecule here that looks like a diene, but if we want to force a Diels-Alder reaction, we could highlight this part as the diene, we could highlight this part as the dienophile, and then we could redraw it in a format where they line up like that, and the charges match up, right? And we could say that this is not an EDG or EWG, but it is... it's not an EWG, it's an EDG. So let's make that pocket between the diene and dienophile. These two groups here are the out groups. This group inside is the in group. This is not an EWG, that's an EDG. So when we draw out the product, right, this is going to be dash, dash, this is going to be wedge, wedge. And now for this one right here, because this is not an EWG, this is an EDG, it does not follow the Endo rule, right? You can say it kind of does, because the Endo rule states that the outgroup is cis to the EWG. And because this is not an EWG, we're going to make that trans like that. Right, but there is a ring here with a double bond right there as well. Plus minus, like that. So this is what I would say is the product for this problem here. Where if I highlight it, like this is where the diene part of the molecule was, this is the dienophile part of the molecule, this is atom 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Any questions on how I got this Diels-Alder product here? Can the methyl also be pointing down? This methyl right here, like the dash? Yes. So if it points down, then that would follow the exo rule, right? Because the Endo rule states that the outgroup is cis to the EWG. So because this is not an EWG, this is an EDG, it's going to be trans to the outgroup. If, however, like this group was an aldehyde, let's say, an EWG, then the Endo rule would have that aldehyde, the EWG, going down cis with the outgroups like that. But because this is an R group, which is not an EWG, it's an EDG, it's going to be, like, based on the Endo rule, I would say trans to those outgroups right there. Why does the ring not have dashes? Oh yeah, so these are... So this bond here does not have a dash or wedge because this bond has an sp2 carbon, which is flat and planar. But we could say that there is a dash bond here technically because this bond is wedge. So this is sp2, sp2. Yeah, so I guess you could say this bond is dash, but you can basically leave this as a flat bond as well, and then that would still make sense. But if you draw that as a dash bond, then you would still get a correct answer for that. Can you attach the methyl at position 6 to position 5 instead? Oh, yes. You could attach... Well, actually, you cannot, right? Because position 5 here does not have the methyl group. And that's why we can't put the methyl group here, because there's no methyl group on position 5 right there. We can't like flip it upside down, because if we did, there's a CH2 in between these two methyl groups. Like these two methyl groups here have to have the CH2 between them. If we put the methyl group here instead, right, then this would be a CH in between them instead. But what you can do is you can flip this dienophile upside down, like this, boom, boom, to get this F products here. And this is gonna be atom 1, 2, 3, 4, 5, 6 with heat gives us this product. Dash, dash, wedge, wedge. Atom 5. It's gonna be wedge methyl down there. Let's try to bring like that. Okay. Plus minus. So is this identical? Let's see here. Wedge methyl flipped upside down. Yeah. I guess this is the other product here. Yeah, so this is a weird one here. So I would say these two enantiomers, I would say is the answer, like that. Yep. Okay, let's move up to the last one, which is this one right here. So we have a very clear dienophile with 2 strong EWGs, which is this one right here, with these 2 strong EWGs. And we do have a diene here, but this diene is an S-trans diene, and we cannot rotate that single bond to make it S-cis diene. So this is going to be no reaction, because Diels-Alder requires an S-cis diene reacting with a dienophile, right? This right here is an S-cis diene, but this configuration here is an S-trans diene, and because this single bond right here is stuck in a ring, and we cannot rotate that bond to the S-cis configuration, this is going to be no reaction, right? Because S-trans diene will not give us a reaction for Diels-Alder. Okay, any questions on that? Okay, let's move on to 8B stuff. Yes, of course. Madison, Jenna. Yep, have a nice night. You guys have any questions or problems? You just want to go for 8B?
Can we go over quiz 4 question 1D?
Quiz 4 question 1D. Okay. Let's see. This quiz 4. One D. This one. Okay. Let's see what's going on here. Let me copy this question over here. Okay. So we have 2 equivalent of aldehyde, CH3, CH2, ONA, which I'm going to draw out as this because it's easier for me to see and read. This is the ethanol solvent in 0 degrees Celsius. So we don't have high heat here. Right? Now, we have two equivalent of the aldehyde. We have a strong base as the reagent. So that means that we're going to look for the most acidic hydrogen in this molecule here. Which hydrogen would you guys say is the most acidic hydrogen we are going to grab?
Alpha carbon.
Yes. We're gonna draw out that alpha hydrogen out to deprotonate the alpha carbon. This strong base here is going to grab that hydrogen, and since this is not a mechanism problem, you don't have to worry about the resonance structures here. We're gonna generate the enolate ion here. So usually, if this was a mechanism problem, you would push this bond between the carbon and hydrogen to make a double bond here, pushing this double bond into the oxygen to create the enolate ion. But that is very misleading because you will get negative charge on the oxygen, but that's not the nucleophile. The nucleophile is going to be the alpha carbon. So instead, I'm just going to give the alpha carbon a negative charge right away, right? And that's going to give me this intermediate here, where there's a negative charge on this alpha carbon right away, just like that. And that clearly represents my nucleophile, which is this alpha carbon right here. Now, I'm going to bring in my second equivalent of the aldehyde, where can you guys find an electrophilic carbon here in the second equivalent of the aldehyde?
The carbonyl carbon.
Yep, carbonyl carbon. So describe to me what the mechanism would look like here from this nucleophile and this electrophile.
So the star would attack the dot.
Yes, star attack the dot, but there has to be something else that happens as well at the same time.
Oh, and then one of the double bonds on oxygen forms a lone pair. Or like a negative charge.
Yes, a lone pair and a negative charge on the oxygen. Right? Because before it has 2 pairs of electrons, it's going to gain another lone pair of electrons and a negative charge, like that. Right? So we're going to get... Okay, I'm just going to draw it like this, where this is the starred molecule. This is the neo bond between the star and dot molecule. Neo bond right here, which comes from this pair of electrons. This dot here, it's attached to this bulky R group, CH2, CH2, and then this alien-looking arm thing, and it is also attached to a single bond O- now. It is attached to the hydrogen as well, but I'm gonna make that invisible so it's not overcrowded. Right? Now, what do you think is gonna be the next step here?
Would the negative charge on oxygen do resonance?
Resonance? So what hybridization is this carbon? SP, sp2, or sp3?
sp2 or sp3.
Yes, because of that invisible hydrogen right there. It has 4 bonding groups, 1, 2, 3, and it can't do resonance with anything else. So we can't do resonance there. We can't make a double bond right here.
Yeah.
Right.
It would be what's the second part of the CH3 CH2OH would go and well, the oxygen would grab the hydrogen on that, right?
Yes, we're gonna protonate the O- with the proton source we have, which is the CH2 CH2OH. It's not water, H2O, like we're used to saying with like NaOH and water, but it's ethanol this time, right? And this gives us our final answer with 0 degrees Celsius. Why do we stop here with 0 degrees Celsius? What is the name of this reaction here? When we have an aldehyde next to an alcohol.
Aldol condensation.
Yes, aldol condensation. So we stop here because we are in 0 degrees Celsius, right? So that is the answer for this first box right here. But once we add heat, what is the reaction?
It forms a double bond.
It forms a double bond between the alpha carbon and beta carbon, and we get rid of the alcohol like that, which is gonna give us this.
Is this through tautomerization?
Not tautomerization because we don't have an enol here. It's aldol, not condensation, but aldol
Oh, dehydration.
Yes, dehydration with heat, which creates this alpha beta unsaturated carbonyl right here, like that. This is not a mechanism problem, so we didn't have to worry about that. But let's just do it for practice. Like, what would happen next? I'm gonna give you a hint. I'm gonna draw this out.
Oh, so the oxygen would grab that hydrogen, right?
Yep.
Okay. And then that would move the bond to it would move the bond up, and then a double bond on oxygen would also move up.
Yes, you can do that, right? So let me just actually do that. But what do you know about what we just formed? What is the name of this ion here? Well, actually,
is it enolate?
Yeah, enolate ion. Right. Okay. Oh yeah, and then there's one more step here. To go from here to here. But that one step has like 1, 2, 3 arrows.
Oh, it's the negative charge moving down, and then that double bond moving down, and then that kicks off the OH.
Yeah. And that's our final answer right there.
Oh.
Okay. But let me double check that, because I didn't check the key yet.
I think that was right.
1, 4. Okay, nice. Yes, it was. Nice. So the first reaction here is Aldol condensation, which we stopped at the Aldol product because we did not have heat to go with it.
Yeah.
Once we add heat to that, we do Aldol dehydration to get to the alpha beta unsaturated carbonyl, the enone, like that.
So if it was a predicted product, just straight, like without the 0 degrees, and it was just heat, then would I do that star dot thing that you told me about?
Yes, you could do that. We could do that technique as well, the star dot technique, which is way faster than doing the whole mechanism. So I just did the whole mechanism, which would like waste time, and I don't recommend doing that if you know the star and dot technique. But you kind of have to do it if you don't know that technique. So let's do that technique here. Right, so we have 2 equivalent of it, so we could draw out those 2 equivalents, where this is the star, this is the dot. And describe to me how we would do the star and dot technique here.
So the star would attack the dot. And and then you have to copy and paste the nucleophile, and then you draw a new bond from there to the dot, and then that would be a double bond, and then the hydrogen becomes invisible, and then you just connect all the extra carbons.
Yes, but with this double bond here, that's if we have heat. But if we're just predicting the product with 0 degrees Celsius, there's no double bond there.
Oh, right. Yeah.
Right? With 0 degrees Celsius, there's no double bond there, and there is something else attached to this dot now with 0 degrees Celsius.
OH.
Yes, and that's the final answer with no heat, right? But the one that you were thinking about was with heat, where there is a double bond between the star and dot, and no alcohol, like that.
Yeah. Can I tell you how I initially did this question, or can I show it to you?
Yes, you can show it to me.
Okay. Let me just send it because it's on my phone.
I have a question regarding this. Just to clarify, whenever you connect the star and the dot, the O double bond, like the carbonyl, that disappears, or is that like a whole new?
So double bond carbon of the star molecule always stays the same. Nothing touches that carbonyl. But the carbon double bond oxygen of the dot always changes.
Okay.
Right? And there's 2 types of reactions here. There's Aldol condensation, which is the one with no heat, 0 degrees Celsius. That's Aldol condensation.
Right.
And there's Aldol dehydration with heat. Aldol condensation is going to convert the carbon double bond oxygen into the carbon single bond OH.
The OH. Okay.
Yes. And if there's a single bond OH there coming from the carbonyl, there's no double bond here. It's just a single bond between the
Right.
star and dot. But if we do aldol dehydration with heat, then the
That creates the double
carbonyl
bond, right?
gets rid of it entirely. Like
Okay.
it's not there anymore. But we have to put a double bond right there between the star and dot.
Okay, perfect.
Yes, that's the
Okay.
star and dot technique to predict the product quickly. We're doing the whole mechanism on predict the product.
Is there another like problem maybe you have that we could practice? that
Yes, let's
in?
practice this technique here. Well, let me see what Jenna did first, and then I'll give you guys another problem to try, and then I'll move on to 118B after that. And oh yeah, Nikki, we could go over your UC Berkeley OChem as well. I saw that you sent me the notes earlier, but I didn't have time to look at it yet. But you could just send me what problem you want to go over, and then we could go over that, and then I'll see it. I'll see it.
Thank you.
Huh? Of course. Okay, let me get my phone really quick. I'll be right back. So, let's see what Jenna did. Oh yeah, and Layla, for 118B, what did you want to go over today for today's office hours? Like any topic, concept, problems you wanted to go over for 118B? Okay. Oh, I see what you did, Jenna. You used the OR minus right here to directly attack the carbon, right? So
Yeah.
that is going to be true if we do not have an alpha hydrogen present, right? Because this carbon here is an electrophile because it's partial positively charged. So this OR minus here would attack that if there was no alpha hydrogen present, right? But because this alpha hydrogen is present, there's a competition of reactions here. An acid-base reaction versus a nucleophile electrophile reaction. Which one is faster, acid-base or nucleophile electrophile?
Acid base.
Yes, acid-base. And that leads to the aldol condensation product with 0 degrees Celsius, no heat, or aldol dehydration product with heat.
Oh.
But if there, let's say there was like no alpha hydrogens there, like let's say there's 2 methyl groups right there, right? Then what you did would be correct, and that would form a like hemiacetal, you would say.
Yeah, okay, because just seeing the reaction, I struggle like figuring out what mechanism to do or like what kind of reaction it is.
Yes, because it's a lot of the same nucleophiles and bases, right? But the
Yeah.
electrophile or reactant starting material changes up what the reaction is, right?
Okay.
Do you remember that chart that I gave you that summarizes the reactions at the end, like with the table
Yes.
of charts right there?
I was looking at that
Yes.
just now.
Did you see
Yeah.
the one with 0 like alpha hydrogens? It gives you that the geminal diol hydrate or hemiacetal or something like that. But the one with alpha
Oh.
hydrogen gives you the aldol condensation
Okay.
aldol product,
So
right?
we just always have to look at the alpha hydrogen.
Yes, if it's present, then we deprotonate that.
Okay.
If it with a strong base present like that,
Mm-hmm.
right? But if you had like this, what would be the answer instead? What would be the product instead?
Would it be like an imine?
Yes, imine.
Okay.
Correct. Where to predict the product quickly, copy paste everything, substitute the carbon double bond oxygen with the carbon double bond nitrogen, and it's R group like that as the final answer
Okay.
for the imine, right?
Yeah.
Okay.
Okay.
Now, Jenna, Madison, I'm gonna give you this product, predict the product to practice with, and then I'll move on to Nikki's problem and then Layla's problem after.
Thank you.
Yes.
Madison, I have a question.
Yes.
Indians and Indians aren't gonna be on the quiz, right? Because we did that last quiz.
I don't think so.
Okay, good.
I'm waiting for her to release her thing tomorrow.
I know. Yeah.
I
She
hate
does
that
it
it's
really
like-
late.
Yeah, it's always like 2 days before.
Yeah, not very helpful, but
But yeah, I don't know.
I
I'm
don't think it would
struggling.
be.
Huh?
Yeah, that I feel like that would be too much if she added that.
Yeah, I'm not 100% sure what exactly is going to be on there. Um, I'm a little confused, but
Yeah.
You guys feeling worried about this upcoming quiz like the most, like compared to the other quizzes this quarter so far?
Yeah, I feel like it just keeps getting worse.
Oh my gosh.
yeah, I'm always worried, but I don't know. I feel like I've been trying to understand this stuff and it's like not clicking still.
You
Yeah.
I
guys
get
just
the Fisher project, what is it? The Fisher
share projection,
stuff?
carbohydrate, sugar,
I get
closing
that
stuff.
stuff more, I think, better than like this.
Yeah, that is like more biochemy stuff. I think you're more of a bio person.
Oh gosh.
Yeah. Uh-huh. Okay, here are problems for you guys to try out. Here's the starting material, and here's the first reaction, and after that, do the second reaction. You could do the shortcut, or you could do the whole mechanism for practice, right? Whichever one you guys want to practice, or both. And I'll check you guys' answer at the end. Okay?
Okay.
Yes. Okay. Hey, Nikki. Are there any problems that you wanted to go over in today's office hours, or concept you want me to explain to you? Emailing them now. Okay. Layla, did Helix finish material for midterm 3 yet? Or next week? Or is he still lecturing on stuff for midterm 3?
For this problem, is there just one equivalent?
It's gonna be 2 equivalent.
Okay,
Yeah, 2 equivalent.
thank you.
And I'm gonna give you guys another product of reaction where there's only 1 equivalent of each. One. One. And same set of reagents like this. Here's another one for you guys to try out. 2 equivalents of the starting material, 1 equivalent of the starting material, and 1 equivalent of the starting material reacting with each other. Okay. Okay. See it? Okay, was it the starred one that you wanted to go over, Nikki, and the question marks that I see on the worksheet?
Yes. Do
Okay,
you want
okay.
me to send you like a blank copy of it? Or
Oh, yes,
Okay.
please. Yeah,
Okay.
that would be great. Uh-huh.
I'll send it.
Mhm.
Okay, I just sent it.
Okay, okay. Let me see here. Right here. Fill in the boxes in the synthesis schemes below, which will show 2 possible options for synthesis of starting material used in reaction A. Okay. So we see that our end goal is to get this acyl chloride, which is a carbonyl attached to a chlorine halogen, which is the functional group acyl chloride. And we see R1 is present like from the end molecule and the starting material. So I'm going to highlight that in yellow to show that that's the similarity right there. And I'm also going to show that this starred carbon right here that I'm starring right now is going to be there throughout the mechanism or synthesis as well, which is this starred carbon right here. Right, now we have an alkyl halide here, a haloalkane here, which when we react that with Mg, that's going to give us something called a Grignard reagent, or MgBr, which is going to look like this, R1 MgBr. This is still my starred carbon right here in red. The magnesium here, Mg, just inserts itself between the carbon and bromine to give MgBr like that. This reaction here shifts the polarity of this carbon because it was partial positively charged because it was attached to this highly electronegative halogen. But now, when it's attached to the magnesium, you could think of carbon as being more electronegative than the magnesium, making that carbon partial negatively charged. Right? So when you see a Grignard reagent, think of the carbon directly attached to the magnesium as always negatively charged, and that's going to be your nucleophile.
Okay, it's the carbon anion, right?
Yes, this is the carbon anion. Think of that carbon with the negative charge as the carbon anion, carbanion, and that you could generally think of it as an R minus reagent, right? Where the R is like whatever this R group is, any random hydrocarbon chain, and we could attack any electrophile with that R minus and attach that R onto that molecule. And that's going to be used with this Grignard reagent here, like that. Okay, now we want to get to the carboxylic acid here. Well, first, do you know what reagent converts a carboxylic acid into acyl chloride? Let's get this out of the way first.
Yes, SOCO2.
Yes, SOCO2. So that's just a reagent that will convert this carboxylic acid to the acyl chloride right there. But now let's figure out how to convert this Grignard reagent into this carboxylic acid right here. We know that the starred molecule is that starred molecule right there. And we see that, let's say, this carbon here attached to the red star was the electrophile in this reagent right here. Right? And we could say that this was the new bond that was formed in the synthesis somewhere. The new bond between the star and blue dot right there. Because whenever we use a Grignard reagent and we use that R minus to attack something, the MgBr ions just dissolve away in the solution. It disappears in the solution. Whoa. Okay, yeah, it just goes away in the solution. So there is one reagent that we could see that does that, which is going to be, let's say, CO2. Right? Because this carbon here, it's partial positively charged since it's attached to these two electronegative atoms, right? So when this R minus here attacks this carbon right here, it's gonna push one of the double bonds of the oxygens to the oxygens, creating an R minus. So we could draw that intermediate out like this.
Oh, so it'll become like a carbonate, right? Carboxylate.
Carboxylate, correct. Right, where that's the red star connected to the blue dot. That's the new bond between them. And that blue dot is attached to one carbonyl. It's no longer attached to another carbonyl because we popped that double bond onto the oxygen, creating that carboxylate, like you said, an O minus, which is going to convert into the carboxylic acid with acid workup.
Oh, okay. I thought you had to use already like a carboxylic acid already as a reagent. I was getting so confused.
Yeah, like you thought like you had to start a carboxylic acid and connect it somehow, like
Yeah,
this
and
positively charged thing. No, 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 we don't do that. Yeah, they want the CO2 as the reagent instead.
okay.
Did your professor go over that in lecture?
She
Lecture notes?
has, but she
Uh-huh.
goes over. It's like
So
so
fast?
much, you know.
Okay, okay.
Yeah,
I'm gonna check your lecture notes and see like how much material is gonna be on the midterm. Is this the first
yeah.
midterm this semester or a second
Ye-
midterm?
This is the first. Her midterms are late in the semester.
Mm-hmm.
So like the second midterm is only like a week before the final, but you only need 2 out of the 3 exams.
Oh, so one gets dropped. Like the
Yeah,
lowest one out of like the midterms and the final gets dropped. That's interesting.
yeah.
Dang. Okay, okay. Interesting.
She calls the final like basically just like a second midterm, like
Uh-huh.
makeup for it, because I
Yeah.
think it's like only 1 lecture difference.
Okay, okay. That's good. That's good. Oh my gosh. Yeah, the system is so different from UC Davis. Mhm. Okay. Yeah, 15 weeks, right, for a semester? 15 weeks?
Yeah, 15
Okay,
weeks.
okay. Yeah. Okay. What do you think is gonna happen to this halo alkane and this NaCN?
I'm kind of thinking that this is also like a carbon anion. Like the carbon is the minus because like we have a metal ion, so it's just like a plus that's
Uh-huh.
balancing that charge. And I'm
Yeah.
assuming that it's gonna attack that carbon that's attached to Br because Br is
Yes.
a good leading group.
Yes, and kick that leaving group off, right? And it is a carbon with an anion because whenever you see sodium or potassium, most likely it's positively charged as a sodium ion or potassium ion, making whatever is attached to it negatively charged. So we have Cn minus here as a nucleophile, which is going to attack this electrophile, like you said, and kick out that leaving group, right? And that's gonna give us this. Oh my gosh. As the product, and like you could draw out the Br minus, but I don't know if that's graded. But just in case it's graded, and I would include that side product as well, just in case. I don't know if it's graded or not.
Okay.
Do you have the key for
Wait.
this so for us to check the answer afterwards?
I don't have the key for this, no.
Okay, okay, that's good.
It
Will
is-
she post the
this-
key later or no?
Yeah, she'll post the key Thursday morning.
Thursday morning. Okay, sounds good. Sounds good. Mhm.
Out of curiosity,
Uh-huh.
how would we draw out the carbon to the nitrogen? Because I know that she has like a specific format, like with the triple bonds.
Oh, right. Like this carbon to nitrogen right here. You can draw like this if you want.
Okay.
Wait.
Is it okay?
It's
It's okay
required.
if we have it bent to the R1 though, that last carbon, right?
Oh, like this? Are you talking like this?
Like I'm talking about if we had it in like one line notation and the carbon wasn't showing. How
Oh,
does it have to be
yes.
fully straight?
You could do it like this as well.
Okay, gotcha.
Yeah,
Thank you.
that is also acceptable like that. But make sure it's linear because the triple bond is 180 degrees and it's linear like that.
Okay.
Right. Now, have you learned about the reaction that converts? Like, if I highlight this carbon here in purple of the CN, that's gonna be that carbon there of the carboxylic acid. Does that reaction sound familiar to you, Nikki? Like how we convert CN to carboxylic acid?
Yes, it
Uh-huh.
does sound familiar.
Yeah. Okay. Do you remember the reagents that does that specifically?
I don't remember the reagents, no.
It's okay. It's okay. It's okay. I'll give you the reaction name and might ring a bell. Hydrolysis of nitrile.
Oh, okay. So we're just gonna use H2O.
H2O.
And then a either a strong acid or a strong base.
Yes.
I'm
Strong.
thinking it's gonna be MEOH or no, or HCl.
Yeah, H2SO4 or HCl, strong acid.
Okay.
Right. With heat, because this is one of the weaker carboxylic acid derivatives. Does that sound familiar? The carboxylic acid
Yes.
derivatives like azo halide, anhydride, ester, amide, nitrile. This is the weakest one, so we're gonna need heat here to proceed with the reaction, right? The top two most reactive derivatives, azo halide and anhydride, they do not require heat. They do not require acid or base. They just need water to do hydrolysis to convert it to the carboxylic acid, right? But because this is the weakest slowest derivative out of all of them, it's gonna need a lot of help. It's gonna need an acid catalyst and heat to push the reaction forward towards the carboxylic acid like that. And I'll go over that in our sessions like in detail, right? But here's just the reaction that converts that nitrile into the carboxylic acid, and that's how we get to here.
Okay.
Yeah. Okay. Now, one of the reactions described in the research article is reaction A. Draw a curved arrow mechanism. Okay, let's see what's going on here. We have this group, which is this group. We have R1. And this right here, automatically, I'm thinking is my base. And this right here is my conjugate acid. Now, this is going to talk about what I just talked about. This is an acyl halide right here, more specifically an acyl chloride, because the halogen here is a chlorine atom. This is the most reactive derivative, where this carbonyl-carbon here is extremely electrophilic. It's so susceptible to nucleophilic attack. Like, it's so positively charged, it attracts like a lot of nucleophiles very easily, right? Now, if this is our products here, right, I'm gonna highlight this part of the molecule in yellow like this, which is this part of the molecule in yellow like that. And I'm gonna highlight this whole thing of the molecule in blue like this, which is this whole thing of the molecule in blue like that. And you notice how this is the new bond that was formed between those two molecules. Like, this is the bond right there that was formed between them.
Yes.
I'm gonna make a disconnection there to show that this chlorine here just leaves as a leaving group, but this alcohol here is my nucleophile.
Okay.
That would attack this carbonyl-carbon and pop this double bond onto oxygen like that to conserve the octet role. Right?
Okay.
If we try to
We
make,
could.
yeah,
We should definitely make sure that like we just break the pi bond instead of just immediately kicking out the chloride, right?
yes, do not immediately kick out the chloride. Kick out the pi bond first onto the oxygen.
Okay.
Yes, don't click out the chloride immediately. Right, that's gonna come after.
And then also, would we would use the base to deprotonate the oxygen?
Yes, this oxygen here, because when we like do this attack, what charge would this oxygen have? Let me actually draw it out and then show you this really here, right?
Okay.
So I'm gonna say this is, I'm gonna draw it the same format as this right here. This is my dot, but I'm gonna flip the carbonyl upside down, and my R1 is gonna be here now. So I basically flipped it upside down and flipped it to the side, right? It's not a carbon double bond oxygen anymore, but it's a carbon single bond O minus, and it's still attached to the chlorine right there. This right here is a new bond between that oxygen attacked it with one pair of electrons, and everything else copy and paste right here. Okay, now if we look at this oxygen here with 3 bonds and 1 pair of electrons, what form of charge should this oxygen have?
It should have a +1.
Yes, plus charge. And like you said, we're going to use this base here to deprotonate that positively charged oxygen to make it neutral, right? That's going to be the base's job right there, right?
Is there...
Uh-huh.
Sorry.
Yeah.
I thought we would deprotonate the oxygen first, or is it okay to deprotonate it in the second step just because it's so electrophilic?
Yes. So we're not gonna do this first. We're gonna actually do something else before we do that. There's gonna be a reformation of a carbon double bond oxygen bond, carbonyl, and kick out the chlorine first as a leaving group.
Okay.
Right there, right? And that is just to reduce the formal charges we have in the molecule, because formal charges makes molecules so unstable.
Right.
So yeah, the images in Notability, sometimes whenever I write on it, it always glitches automatically.
Oh, if you tap on it, yeah.
Yeah, when I tap on it. So if it's possible, next time, can you send a PDF version of it so it doesn't glitch out like this? If you have a PDF version.
Oh yeah, of course. Yes.
Thank you. Positive charge. Carbonyl, R1. So now we have Cl minus right here, which you might ask, why can't we just use the Cl minus to deprotonate this positively charged oxygen to make it neutral to get to the final answer, right? Do you know the reason why? Did your professor go over that? Why?
Yeah, it's a really strong acid, which means it's a really weak conjugate base.
Yeah, really weak conjugate base right here. It's not gonna be as reactive, right? Because this chlorine minus here is so stable by itself, like it's so electronegative, right? And if it
Right.
gets formed, this is more of a lab thing, like in the field, but this is gonna form very toxic HCl gas, very toxic to breathe,
Okay.
right? So that's why we use another base like pure, like this nitrogen compound here as a base to grab that hydrogen. The bond between the hydrogen and oxygen being grabbed, those 2 electrons of that bond go onto the oxygen, giving that oxygen another pair of electrons and making it neutral.
Okay.
Yeah. Okay.
I think. Okay. Yeah, I think that all makes sense. I guess the only thing that I was just a little confused on was just the protonating or the deprotonating the oxygen with the
This
base.
part right here,
Yeah.
this one right here, the last part.
No. Yeah. Yes, that one.
Mhm.
So I always assume that you want to make your nuke a better nuke, but if you have a good base, because isn't like an amide a really good base?
Like this amine right here.
Yeah, like what I did at first is I used that to take the H, deprotonate it, and then I made it in a concerted step of like also attacking it, but I think that might be wrong because this isn't like enzymes.
Oh, are you attacking this positively charged oxygen here like that? Or what?
Yeah, like in the very first step, I deprotonated the hydrogen.
Oh, like very first step, like you deprotonated the alcohol right here.
Yes.
Oh, that's what you did.
We don't have to do that because we already have a strong electrophile, right? That's why we're allowed to wait. Okay.
This, I know what you're thinking about now. Because if we had an ester, let's say for example, with an OR, this is not a strong electrophile. That is a weak electrophile, right?
So we need a strong nuke then.
Yeah, we need a strong nuke. Right now, this is a weak nuke. To make this a strong nuke, we gotta deprotonate with the base, right? Yeah, that's good. That's good. This is not required because this is a weak nuke with a strong electrophile, which is gonna do the attack right away. Like that.
Now, if this was like a ketone, which isn't as strong, would we still do that or no? Would we have to like deprotonate it first or no?
Yes, if this was a ketone is not a strong electrophile as well, right?
Okay.
This
so
is
sorry.
Yes,
or like what about like an anhydride as well? Would that work?
Yes, anhydride would work. Anhydride is a very strong electrophile. Like those top 2 ones, like anhydride and acyl chloride are extremely reactive, extremely strong electrophiles. Yeah.
Gotcha.
So they can react with the weak nucleophiles, anhydrides and acyl chlorides. Those top 2 right there. Those 2 derivatives. Right. Nice. Dang. Okay, you know that concept already. That's good.
Yeah.
Okay. Yes, and that's how we get this structure and the Cl minus floating around.
Okay.
Nice. Okay, last one here. Reaction A could possibly lead to a mixture of several products, not just the one shown in the mechanism scheme above. Draw a competing product constitutional isomer that you predict could form and propose a reason that could explain selectivity for the formation of the product above instead of the one you drew. A possible competing product constitutional isomer that could be formed in the reaction above. Selectivity for formation of the product above instead of the one drawn out could be predicted based on pictures and a few words. Okay, let me think about this.
Yeah, I was a little confused on because I didn't see any other like carbonyls in here.
You notice this is the nucleophile right here that attacked this electrophile, which is an alcohol.
Yes. Oh wait, could our base just deprotonate it and that be done with, or no?
No. Don't think about the base deprotonating it. Do we have any other alcohols in this molecule?
Yeah, in the R we do.
Yeah. Yes. Oh, this is an ether here. So ether is not as reactive.
Or no, I mean like just in the R group.
Yes, in the R group right here. Right. The whole entire R group. This one right here. Right?
Yeah.
So we could have used that alcohol to attack that structure to give us this product.
Oh, I see.
Right here. Like that, right? Where this is the oxygen right here, and that could have been the product. So there is one very big factor here that makes this the minor product and this the major product. Can you think of a factor that makes this more favorable? Like what makes it an easier time for this alcohol to attack this electrophile over
Would it be sterics?
these steric hindrance? Yes.
Okay.
Steric hindrance. So that's my guess, but we'll check the key when she
Okay.
releases it on Thursday. Steric
Yeah.
hindrance, right? Because it's so crowded here, right? Like it's so many groups floating around like that.
Okay.
Mhm.
Gotcha.
Yeah, but we'll see on Thursday.
Okay. Thank you so much for helping me with that.
Yeah, of course, Nikki. Yes. Yeah, you said your midterm is coming up when again? For
It's Tuesday morning.
Tuesday morning. Next Tuesday morning. Okay, so 1 week from
Yeah.
now. Okay. That's good to know.
I'm gonna grind OChem
Yeah.
all weekend. I have a bio midterm on Thursday, so I'm like kind
Oh
of
my
pausing on
gosh.
OChem.
Yeah, I know. How many units or like credits are you taking this semester?
I'm taking 13, which
Mhm.
I take a pretty light load actually, but
You have a lot of like extracurriculars, like lab research and everything.
no, not yet
Not
actually.
yet, yeah. Oh, it's true, because your sister told me like you went to like a lab like conference like
Oh, we went to Abercamps and Sackness. I did an internship during the summer.
yeah, I see.
Yeah.
Yeah, and Farrah had like trolled you, like was messing with you.
He did. He came up to me. I didn't know who he was, and
Yeah.
he was asking me about like SNR and how like we can like chemically like make them, and I'm like, oh, like they just come like this. Like I don't know how I'm like count count which the groups and everything.
Yeah, I know.
But
Yeah, it's funny.
could I also ask you one more question?
Yes. Mhm.
With the Grignard reagents, are we only allowed to attack like pythons, or could
No. You could attack haloalkanes. You could attack epoxides. Haloalkanes, epoxides, carbonyls. You could attack acids to do an acid-base reaction. So this Grignard reagent here is a strong nucleophile and base. So it could attack a carbonyl, popping the double bond over, or it could open up the epoxide in the left subside, or it could do an SN2 reaction with the primary haloalkane, kick out the leaving group, or it could do an acid-base reaction if there's a strong acid present, deprotonate a very strong acid like that. Right.
okay?
So it could
Gotcha.
be a nucleophile and a strong base like that.
Okay.
Right.
Gotcha. Okay.
Yeah.
Thank you.
Of course. Okay, Madison, Jenna, have you guys tried the shortcut or mechanism for the problems I gave you guys?
Yeah, I'm still doing the second one. I kind of got stuck on it.
Okay. What about you,
Like I
Madison?
did the. Oh, sorry.
Yeah. Go ahead.
Oh, I was just like I gave up on the mechanism and just did the
You just gave up the mechanism and just did the shortcut, like for the first part?
Yeah. No, for the second question.
Oh, for the second part. But did you do the mechanism for the first part?
Yeah.
Okay.
Yeah, I did. I think.
I see. Okay. We'll check your work after soon. What about you, Madison?
I just did the predicted products for both of them.
For
I
both of
already
them?
tried to.
Okay, can you send me and let me see what you got to see?
I just have to start with like the basic stuff. Like it gets too intricate and I just get even more confused sometimes.
With the decoration R groups?
With like the mechanisms.
Oh, the mechanisms.
Like I see the patterns sometimes and like the star and the dots and stuff. Like more than I see in the mechanisms, except for like nucleophilic acyl addition. Like I've got that. I feel like we've done that one so much.
I know, nucleophilic acyl addition. And there's like different ones of them. So star, dot, and you connected them. Oh, so the dot here, Madison.
Oh no.
Is gonna be the carbonyl carbon, not the alpha carbon. The alpha carbon is the star. The dot is the carbonyl carbon. That's the electrophile. Right, but yeah. Right. So you did have the Aldol and alpha and beta saturated carbonyl as the products. Yeah, for both of them. But the dot is at the wrong location, right? The dot is not at the alpha carbon. The dot is of the carbonyl carbon.
And then the star's at the alpha carbon?
Yes, the star is at the alpha carbon, right? So if we did it, this is the star at the alpha carbon. This is the dot at the carbonyl carbon.
Oh, I see.
So if we make a new bond between them, nothing happens to the star molecule. Everything is just copy and paste of the star. This is the new bond between the star and dot. The dot here is attached to, if this was no heat, this R group. And an OH. On not that carbon, but this carbon right here, on the dot carbon.
So the star attacks the dot?
Yeah, or yes, the star attacks the dot, making this new bond right here.
Star attacks dot. Where? Okay, I think this is where I'm getting confused. The carbonyl carbon, the one with the rest of the reagent attached to it, or the rest of the molecule attached to it, which one is that? Is that the star or is that the dot? That's the
This
star.
part or this part here?
The bottom part.
The bottom part is the star molecule. This yellow highlighted part here, the starred molecule, is this whole yellow molecule here. Nothing touches that molecule. Everything else is copy and paste, right? Everything is like there for the starred molecule. But this one here, the blue molecule, is this right here, where something did change, right? Because there's no more carbonyl. It's a single bond OH now with no heat.
Okay.
Right. But once we introduce heat, this is what we get. No more alcohol. And a double bond between the star and dot, like that. Where this is the blue molecule right there. Like that. Right, so the starred molecule in yellow here always stays the same for both reactions, aldol condensation and aldol dehydration. But aldol condensation has a single bond OH and a single bond between the star and dot. But aldol dehydration with heat has no the carbonyl anymore, no OH, nothing there. It's gone, and a double bond between the star and dot with heat. Yeah. Okay. Yes. Okay. Let me check Jenna's work.
I did that so wrong.
What is this here?
So wrong.
Let's see. Oh. No. So once you form the enolate ion, don't protonate that. Like, that's gonna go down and have the alpha carbon attack the carbonyl carbon to get to here eventually. Right.
Yeah.
Yes.
Wait,
yes.
okay. Is there a case where we do protonate something like that? Because I don't know why, like, all of them are just getting mushed in my brain, and I can't,
that's why this part of OChem, the enolate chemistry, is when a lot of students get overwhelmed. Like, this is when I got overwhelmed and I was like about to give up on OChem. Like this part of OChem right here. Yeah, I know. Because there's a lot of things that are like very similar and they get mushed up in the brain. But like, we know there's two equivalents of this right here, so that's why we know that the enolate ion is going to attack another equivalent of this molecule. If there was only one equivalent of it, then we would present it.
Like, it always says, or not always, but like she said that it's not always stated that there's two equivalents, so we kind of just have to guess.
Yeah, because on
which makes it harder.
instructions, she's gonna say assume excess, unless otherwise noted, unless it's like one equivalent.
Okay.
Right. So you're
if
always
it's
gonna
one
assume excess.
equivalent- Okay. If it says one equivalent, then it'll be one equivalent. Otherwise, it's always an excess.
Yes. If it's one equivalent and you have excess base, then you're gonna end here. You're not gonna proteinate it because we have excess base, which is gonna stop at here, the deprotonated enolate ion, like that. Right.
Okay.
But you would proteinate it if you tautomerize an enol into a carbonyl. Right. That's when you would do the tautomerization stuff, like in acidic or basic conditions, depending on your reagents. Right. Yeah, it's a lot. It's a lot.
So always assume
Yeah,
that there's two equivalents when it says there isn't. Like, does it
Yes.
say anything about it?
Always assume two equivalent, even if it doesn't say anything. If it says one equivalent, then that's when you know it's one equivalent.
But the thing is, there's other factors to consider. So like even if it doesn't say two equivalents, like there could be other things that would like throw you off. And then like not seeing that two equivalents will make you think that it's something like another reaction.
Yeah, like something weird going on in the molecule here can throw it off.
Yeah.
Right.
Would that table that you made help?
Yeah, that table would help differentiate what the reaction is. I'll show it to you guys again, that table, and I'll give you guys a lot of practice on this to differentiate like the different reactions that you guys are gonna see, so you guys don't get confused tomorrow and on Thursday as well.
Okay.
Right, in office hours. Okay, let's finish off with this one. I'm just gonna do the mechanism here just to show you guys what's going on. We have a strong base, CH3O minus, and we want to deprotonate an alpha hydrogen. There's an alpha carbon here, alpha carbon here, alpha carbon here. There's no alpha hydrogen in there because it has 4 bonds. So we're gonna deprotonate one of these alpha carbons. Doesn't matter which one because it's symmetrical. To generate the enolate ion. And we know that when we make this enolate ion here, the O minus is not the nucleophile. It's this alpha carbon here. So we're gonna reform the carbonyl, have this alpha carbon attack this aldehyde, and pop the bond onto the oxygen to give us this new bond between the star and dot. The dot has an O minus. The star is part of a ring, which is attached to that carbonyl. And we use our proton source here to protonate the O minus to give us our final answer with no heat. And you could see that this is the final answer with the star and dot shortcut technique as well, right? Because this is the star, this is the dot. We made a new bond between the star and dot. The starred molecule here stays the same. Nothing touches that starred molecule. But the dot molecule here, something happened to it. The carbon double bond oxygen became a single bond OH. Right.
But we also changed that starred molecule. We formed an enolate.
An enolate, but it's gonna be reformed when we have this negative charge go back down to make a double bond again between the carbon double bond oxygen and have this alpha carbon attack.
That's just so we can like attach it, right?
Right. Yeah.
Like,
right. So it does get changed. Right. Correct. It does get changed at the beginning, but it gets reformed so that it can attack it, like Madison said, like attack the electrophile.
Okay.
Yeah. Okay. Now you guys know the mechanism for aldol dehydration already, which is the boomerang step. We copy paste and get rid of the alcohol, put a double bond between the star and dot to create us this alpha beta unsaturated carbonyl, like that. Okay. Now this is just homework for tomorrow's office hours. With this alpha beta unsaturated carbonyl that we just formed, she can give you another reaction, right? And let's say that reaction is, I'm gonna give you 2 different things here. Actually, 3 different things here. And I'll check this tomorrow. Yes. So I'll give you guys a hint here. This has to do something with 1.2 addition and 1.4 addition, with the reversible nucleophile and irreversible nucleophiles. Okay.
Oh,
Yes.
I
Okay.
actually kind of like these more.
Yeah, because this one's like you notice like that this part of the molecule, and then everything else is a distraction, and just focus on what's the reversible and irreversible 1.2, 1.4.
Yeah,
Yeah.
like the reagents are also just recognizable. Like you know what to do with.
Yeah, it's more clear
How to add
too.
them on, you mean?
Yeah. Mm-hmm.
What is the like? What do you call the one we were just doing prior to this? Is that that's Aldol condensation
The one with
and
no heat,
dehydration?
Aldol condensation. The one with heat, Aldol dehydration.
Okay.
Mm-hmm.
Okay.
Yes, and then once you get the Aldol dehydration product, alpha beta unsaturated carbonyl, you could do 1.2, 1.4 addition stuff, conjugate addition, direct addition stuff.
Okay.
Uh-huh.
Perfect. Thank you.
Yes, of course, guys.
Okay.
Okay.
Thank
Yes.
you.
Bye.
Of
Thank
course.
you.
Bye. Good
Have
night,
a good night.
guys. Have a nice night.
Bye.
Bye.
Two questions that are like kind of small. They're like
Uh-huh.
clarifying questions.
Yeah, of course.
It was just like in some of my mechanisms, I don't know. I think it's correct,
Mm-hmm.
but I'm not sure.
Mhm.
Can I like send you like a picture of them?
Yes, yes. Mhm.
Okay. Okay, I just sent it.
Okay.
They're really small questions. Sometimes I get like I want to say like I understand the most part of it. I get stuck on like small things and like why.
Uh-huh. Yeah, yeah, those small things in OChem, like those nitty-gritty details.
Those are what get you.
I know. That's very important though. It's like I know, you know.
Yeah. Oh yeah. No, I totally agree.
Yeah, I
But
know.
if you miss them, like those are just like they're like so sad if they get marked down on like exams and stuff.
I know, yeah, the arrow charge, all where you attack, the direction of the arrows as well.
Oh yeah.
Yeah,
Like
I
with
see.
resonance if it's backwards.
Yeah, I know, I know. I see, okay. So this one attacks, boom, O minus. Yeah, what was your cool? Oh yeah, I see what you did here. Yeah, what was the question on this one for C?
For C.
Yeah.
Okay, I was just wondering, should our Grignard reagent also attack these other pi bonds? It shouldn't, right? Like
No. Those pi
okay.
bonds, think of them as nucleophiles, the pi bonds. Nucleophiles react as
Okay, yeah.
nucleophiles. Yeah. Uh-huh. Right, nucleophiles avoid each other. Uh-huh. Okay.
Okay, gotcha.
Next one, B.
For B, okay, so I've never really reacted with like carbon that had like fluorides on it, and
Mm-hmm.
I feel like the only thing I was a little confused on is if I'm using the base correctly.
Hmm. Wait, let me see what's going on here. So this CF3O. Oh. I see what's going on here.
I'm pretty sure I did this mechanism wrong, but
Oh, is the NH2R? Oh, I see what you did. NAD personate that. Boom. Boom. That's good. Very good. Kick that out. Yes, CF3. Okay, yeah, so the mechanism is correct until the last part. The last part you use CF3 as the base, but it's gonna be. Oh wait, actually. Huh. Yeah, it could be that, or if this excess triethylamine, like the starting material, you could use that as the base as well. So you did it correctly.
okay, so if we
Yeah.
have excess in our original base, then we can also just use that.
Yeah, and that would be the better one to use.
Yeah, because it is stronger
Yeah.
versus a carbon.
Mhm.
Okay.
Yeah,
that makes
right.
sense.
And that carbon with the negative charge is super stabilized. Like that negative charge there is stabilized by the 3 electronegative
fluoride.
fluorine. So yeah.
Because they're super electronegative. Okay,
Right.
that makes sense.
Right. Okay.
And
Next.
then for number 8, I was just confused if because I don't remember like the differences between SN1 and SN2. I know like pi bonds are SN1 or yeah. But if it's like a tertiary site, are we still allowed to attack with the nucleophile in like SN2 or no?
Oh, the first thing you did it here. Oh, I see what you did. You protonate that, make that to the good leaving group. So so once we make that into a good leaving group, the OH2 plus oxonium ion, right? That's because we're in aqueous solution, like there's HCl catalyst floating around in water, aqueous solution. That aqueous solution is just gonna grab that oxonium ion and rip it off by itself to form a carbocation. And then that gives us our SN1 mechanism.
Okay. So it should be SN1 then. Okay.
Yes, with the carbocation, right. Okay. Yes.
And then with the rest of the steps, like if once I make that into like an SN1 mechanism,
carbocation?
Correct?
Yes.
Yeah.
But then the nucleophile would not attack like that carbon with the leaving group. It will attack the carbocation.
Okay, gotcha.
Yes.
Okay.
Right.
And then we would just have the chloride take the H back, and then we'd get our catalyst regenerated, and then our end product.
Yes, correct.
Okay, awesome.
You got it. Yeah.
But this is just because it's an SN1 because it's a tertiary site, right? And because it's a solvent, so it's gonna like push forth the reaction, and we have a weak nucleophile, so we need a carbon cation.
It's a secondary carbon because it's attached to two other carbons, which is able to form a stable carbocation. If it was primary, it could not leave. Well, if it was primary hindered, it could do a concerted hydrogen shift, but we don't have to worry about that here. This is secondary, so it could just leave by itself regularly, like naturally, right?
Okay.
And it's also in this aqueous solution with oxonium ion, so it's just gonna rip itself apart, like dissolve away into the solution naturally as well, forming that carbocation.
Gotcha. Okay.
Yes. Thank you. It looks like you have like a pretty good, solid conceptual understanding of a lot of things already, Nikki.
Yeah, I'm mostly good at OChem. I just get like kind of iffy on just small things, and they don't have it as they used to have like office hours like from like 9 to 5 every single day, and now they have like none, and it's so sad.
Oh my gosh, yeah, and you got an A last semester too for OChem 1?
I got an A+.
A+, oh my god, that's so good.
Yeah, I'm really happy.
And then like you just have questions about the small little conceptual details, like the ones you've been showing me. So our sessions are gonna run very smoothly, very like quickly.
Okay.
Yeah.
Great.
Like...
Yeah. Yeah, I know for the most part mechanisms. Sometimes I forget a little because there's so many of them, but for overall, I think I have a good grasp of what's going on.
Yeah, that's good. That's good. And we got like 6 hours before the first midterm for you.
Yeah, shove it all into my brain.
Yes.
All right. Well, thank you so much for helping. I really appreciate it.
Yeah. So first, Nikki, what are you gonna do now? Study more, or like, are you at the library, like UC Berkeley Library, or at home, or where are you right now?
I'm at home right now. I think I'm gonna try. This is like an 8-page packet of problems. So this is our homework. So it's due tomorrow night, and that's our homework, and it's like a practice exam kind of like. She makes us do sometimes before the midterm. She makes us do practice exams, and she assigns them as homework, so we're forced to do them. And then she'll like double up the credit as well, so it's like a bigger incentive.
Oh my god! Wow, for OChem?
Yeah.
Oh, okay.
She's a really good teacher. It's just sometimes she goes really fast, and to supplement it, you need to go to office hours. But because there's just not as many this semester, it's making it like rough.
I know. Oh my gosh. Well, you can come here anytime for office hours, and our private sessions will be way more in depth too for your questions and more practice ones for your class as well.
Okay, great. All right, I'll definitely come tomorrow then. All right. See you, Brian. Thank you so much.
Good.
Have a good one.
Good night, Nikki.
Good night.